I'd like to talk to you about, well, my career as an astronomer and give you some idea of how I got to where I am today and some of the decisions I made along the way. But I'm also going to talk to you about a couple of my areas of research to give you an idea of the diversity of topics that are in astronomy and what you can do as an astronomer if you choose to go down that career path. So I actually got interested in astronomy at the age of 6 when I got woken up in the middle of the night by my father, who took us out into the backyard, and we actually saw Halley's Comet. It was the first time I'd ever seen a comet. I knew about the moon and the sun and understood what they were, but it was the first time I actually saw another astronomical body and actually fully understood that there were other things out there in space. And that really got me interested in space in general. And so when I got to high school, I actually took science subjects. I took biology, chemistry, and physics. I was interested in all three. And when I got to grade 11 and 12, I actually concentrated on physics. I really enjoyed understanding how things work, the forces, how bodies moved throughout the universe, and we actually had a really fun astrophysics component where we looked at things in space, or planetary orbits, things like time dilation, conservation of angular momentum. Those things really interested me. And I also had a female science teacher for both math and physics, so they really inspired me that, you know, a woman could have a career in physics. So when I decided to go to university, I chose to do a degree in planetary science, and planetary science is actually the study of geological processes on other planets. So we were looking at volcanoes on Mars and the surface of Venus and the craters on the moon and the different environments in our own solar system, and I really enjoyed that. But the problem with that degree program is we kept looking at rocks and I have to say I wasn't really interested in understanding how rocks formed, so I actually chose to change my degree at undergraduate level and pursue an purely astrophysics degree. So that's really understanding how those rocks formed the orbits around the sun and the physical processes that actually created the universe. Those were the topics that really interested me. So that's what I did. I ended up finishing with a degree in astrophysics and then went on to study at a higher level at graduate school because I wanted to be an astronomer. And I did a master's degree where I actually looked, I was a member of several teams where we discovered planets around other stars, and I'm going to talk to you a little bit about that later. And now I'm doing my PhD here at Macquarie University, where I'm actually looking at the processes of star formation. So how do the stars in our universe actually form? And so I've had a very diverse career, and hopefully that'll inspire you to continue on and do science during your schooling and education. So I want to talk to you now about star formation, my main area of research. And if you've ever wondered where the iron in your blood or the gold in your jewellery or even the titanium in your smartphone comes from, it comes from stars. If you look at the periodic table, anything heavier than iron is actually created when a massive star dies and blows up in a supernova explosion. So we wouldn't be here today if those most massive stars in the universe hadn't blown up. And so this understanding of how these massive stars are formed is really important because we want to know where do we come from. And so we need to investigate how these stars came about, what triggers the star formation, and what evidence exists in our galaxy for these stars, and how do we actually search for them. And so these are the fundamental questions that we're trying to ask in this area of research. And so where do stars come from? Well, up in the galaxy, we have giant molecular clouds, and these are just big clouds of lots of gas and dust molecules that coalesce and come together under gravity, like this picture here of the Orion Nebula. And this is a very active star-forming region in our own galaxy. And these dust and gas clouds are where all the stars in our galaxy are formed. And what happens is, under gravity, these clouds collapse. And as they collapse, they start forming a disk and get denser and denser and hotter and hotter. And if those of you who are studying physics will probably recognise the term the conservation of angular momentum. And what happens is, as these clouds continue to collapse, they spin faster and faster and heat up in the centre until eventually the heat in the centre is so hot that it actually causes nuclear fusion to take place. And it's at that point that the centre of the gas cloud has become a star. And that's when what we call the birth of a star. And if you're trying to understand this physical concept, think of an ice skater or a ballerina who's spinning with her arms out, and as she pulls her arms in and she's spinning faster and faster, that's what the gas cloud is doing. As it gets denser and denser and more compact, it's spinning faster and faster until that nuclear fusion takes place. So that's really how a star forms. And during this process, we get a lot of things happening around these star-forming regions. So I mentioned that you have a massive young star in the centre of its physical environment. This is deep within the molecular cloud still. And, it's just started on its life. But we have a disk of still gaseous material that forms around that star, and what happens is that disk will eventually, that's full of the debris left over from the star's creation, will eventually form into planets. And so that's how our own solar system formed. When the star was born, all the leftover gas and dust that was still orbiting the star eventually coalesced and formed into the planets that we have today in our own solar system. This diagram also shows you when we have outflows of gas, again due to that conservation of angular momentum. And these outflows tend to contain lots of clumps of different molecular gas. And so when we look at these star-forming regions, we can actually detect different molecules in space. And not just like helium and hydrogen, which are the most abundant in the universe, but more complex molecules like methanol, which is actually an alcohol. And so this diagram really just shows a snapshot of the birth of a young star and the different phenomenon that's going on at that moment, at that time when that star's born. So it's quite an exciting field of research because we can look at the physical environment, we can start trying to understand the chemistry, and really try to put together a picture of how stars in the universe are forming. Now, once a star's formed, it can actually have a different lifetime depending on how big it is, how massive it is when it's born. So this is a nice poster I picked up from Cosmos magazine, which you can find online. And it really shows you the different evolutionary stages of a star. And if you look at the third from the bottom, it says sun-like star, and this is the trajectory that our sun takes. So a protostar is that gas cloud just before nuclear fusion takes place. That's what we refer to a dense gas cloud before a star is born. And then our sun is halfway through its lifetime. It's about 4.5 billion years old. and in about 4 billion years it's actually going to become a red giant. And what that means is it's just going to grow bigger and bigger, and it's actually going to extend out beyond the orbits of Earth and Mars, so we really don't want to be around on Earth at that time. Earth will become uninhabitable. And eventually the Sun will just puff off its extra layers and form a little white dwarf, which is the core of the star, and so that's and it'll begin a sort of a different stage in its life at that stage. Now our star is pretty normal. It's nothing really spectacular is going to happen in its lifetime, and this is sort of the normal trajectory for low mass stars. But what I study are the most massive stars in the universe. These are stars that are at least 10 times more massive than our Sun. They're very rare, they're very hard to find in the galaxy, but these are the ones that go supernova, and they're the reason that we're here today, and that we have all these complex molecules and chemicals today, because it's in that supernova process that all those elements are created. And so if you look at the top of this picture, you'll see that the more massive stars are supergiants right from their birth. And they're blue, which means they're super hot, so they live, they burn very brightly and they live very fast. They have a much shorter lifetime, and then they go supernova, which is what happens when iron is created in the core. You need energy to fuse iron, and so the star runs out of energy, and due to the intense gravitational pull of the star's core, it collapses on itself, and that's how you get that supernova explosion. And sometimes that explosion is so big and the gravitational pull is so strong that you can actually create a black hole. So these stars die very, very violent deaths. But as again this poster shows, you get a lot of debris from these supernova explosions, and these form the next generation of stars because they go back into these giant molecular clouds. So the star forming process within our galaxy is constantly triggering more star formation and is ongoing. And so, you know, it's quite an exciting field to be a part of. So if you're interested in stars in astronomy, then this is the most important diagram out there. It's called the Hertzsprung-Russell diagram, and it shows you not just the evolution of how stars will evolve in their lifetime, but it also gives you an idea of their temperatures, how bright they are, their classification, their masses and their sizes. And I won't spend too long on it. You guys can download it from the internet and have a look for yourself. But you'll notice on what we call the main sequence, which is that main diagonal in the centre of the diagram, in the yellow region you'll see the Sun. So our Sun is sort of sitting quite happily in the middle. And it's a yellow star, which means it's sort of a medium temperature. It's about 6,000 degrees on the surface. The bluer the stars, the hotter they are, and the redder the stars, the cooler they are. And our star, as I mentioned before, is going to one day become a giant. So it'll actually move throughout the diagram up into the supergiant part, where it'll get bigger and bigger in terms of size, not necessarily in terms of mass. And then eventually what it will do is it'll drop down to the bottom part of the diagram where we have the white dwarfs. And these dwarfs are just very small, very compact, bright stars. So this diagram is really important because it provides a snapshot of the evolution of any star. So if you're looking up at the night sky and you see, for instance, Betelgeuse, which is in the constellation Orion, it's that bright red supergiant star. The red tells you that it's cooler, and it's quite big and bright, so you can see where it lies and where it is in its evolution. So Betelgeuse is actually dying at the moment. So all the red stars are actually in their death throes at the moment. So hopefully that's something that you guys can continue to look at when you look at stars in the sky. give you an idea of what's going on in an individual star's lifetime. So the question then is, I mentioned that some of the most massive stars in the galaxy are very rare and very difficult to find. And that's because they're lying within these giant molecular clouds. And these clouds are like the clouds in our sky. When it's a cloudy day, you can't see the sun. So these dust and gas clouds that exist in the galaxy, they block the stars that are lying within them. And so we can't actually observe them with optical telescopes. So we actually have to use a different part of the electromagnetic spectrum. And so we actually use radio telescopes. And these are telescopes that can detect radio waves coming from space. And fortunately, here in Australia, we have a lot of radio telescopes. Australia is one of the leading countries in the world for radio astronomy and has been for decades. And these two pictures are actually two of the Australian telescopes that I've actually used in my research. The picture on the left, taken at night, is of the Australia Telescope Compact Array, which exists out at Narrabri in New South Wales. And it's actually 6 telescopes that are linked together. So yes, we use radio telescopes to look at areas of the galaxy that we can't view with the optical telescopes. And I mentioned before that Australia has quite a few radio telescopes, and these are pictures of 2 of the ones that I've actually used in my research. That's the Australia Telescope Compact Array out at Narrabri in New South Wales, and the Parkes Radio Telescope out at Parkes in New South Wales. And both these are really important telescopes for not just my field of research, but for most astronomers here in Australia. And Parkes is actually a really important telescope because it was the one that received the signal from the moon landings when Neil Armstrong first landed on the moon. So Australia has played a significant role throughout history in terms of radio astronomy and working with countries like America and NASA and the European Space Agency and collaborating and sharing these instruments with each other. We used a range of different telescopes to look for newly forming stars. And that brings me actually then to the next area of research. Not only do we want to understand where we come from and the elements like gold and silver and uranium and iron come from, which comes from those star-forming processes, but it also brings us to the question of, are we alone in the universe? Is Earth unique? Does life only exist here or within our own solar system? And if not, how do we find other worlds? And what would life be like on these worlds? And could we ever visit them? And I actually found this really nice poster from NASA. NASA actually did a series of space tourist posters of what it would be like if you were a tourist visiting the different bodies in the solar system. That's a nice one. So planets around other stars, how do we find them? Well, there's actually several different methods. I don't want to go too technical on you, but I will explain 2 of the methods that we use to detect planets around other stars. We call these planets exoplanets, and they exist outside our own solar system. And probably the one that's easiest to understand is the transit method. So if you're looking at a star and you're measuring its brightness, when a planet that's orbiting it passes in front of that star, it'll actually block some of that light. And so if you look at the graph below, you'll see that the brightness of that star takes a dip. And that tells us then that a planet has just passed in front of it, and we can determine the existence of that planet. And the depth of that dip and the amount of time it takes to pass the front of the star actually tells us about the mass and the orbit of the planet. So we can actually infer some information about the planet just based purely on looking at its parent star's brightness. And most of the planets that have been discovered so far have been via this method. Another method which is actually very useful for detecting much, much smaller planets is actually called microlensing or gravitational microlensing. And what happens is you actually observe a star far away, and a foreground star, so that's a star that's closer to Earth, lies in front of it and will actually bend the light of that background star due to gravity. And if that foreground star happens to have planets orbiting it, we can actually detect this in that process. And I'll just show you a diagram that's probably a little bit easier to understand in the sense that at the top panel, you'll see that the red light is just looking at that background star, but when a foreground star passes in front of it, it acts as a lens that magnifies that star's light, so we get that brightness level, and that's what we're detecting. And the graph shows that magnification and brightness increases as that star passes in front of the background star, and that's what we call a microlensing event because it's magnifying that stellar brightness. And if that foreground star has a planet, we actually get a deviation in that light curve, and see that spike there is tells us that there's a planet, and that's how we detect planets. We're using this method. And to show you some evidence of a recent discovery, I know this is a complicated diagram, so just ignore everything except that little spike in the light curve. That was a planet we detected about 11 years ago actually. I was part of a team and we detected this planet, and we actually worked out that it's about the size of Neptune. So it's about 5.5 times the size of Earth. And at the time it was the smallest planet we detected to date. So that was a project I was involved in earlier on in my career, and it was very exciting to be able to discover this planet that exists around another star far away. Now, a lot of planets have been discovered since then, and since I think last week we have just over 3,400 planets around other stars. And this is a poster that I pulled off the web. It's actually just a snapshot of only a few of those planets that have been discovered. But every time we discover a planet, someone does a drawing, an artist's impression of what that planet would be like based on what the scientists have discovered. And so what you're looking at here is the actual sizes of these planets in relation to each other, and the colours kind of indicate what their chemical composition could be like, or their surfaces. Some of them are gas giants like Jupiter and Neptune, others could be more rockier like our own Earth. And if you look at the left-hand side, buried there is actually a snapshot of Earth. So you can see Earth is actually quite small compared to a lot of the planets that we're discovering around other stars. So the two methods of detection that I've just quickly explained are really only able to detect very massive planets like Jupiter. And so one of the drivers of this field of research for astronomers is we want to detect Earth-like planets, smaller planets, planets that may have liquid oceans of water, and then therefore, could they then host life? And so that's really what's driving this field of research. And so those are, I know I've gone through quite quickly, but those are my two main fields of research. So star formation and the search for exoplanets. And that just really represents a snapshot of the diversity of topics that exist in astronomy. I've been fortunate enough that as an astronomer we tend to lead quite international careers. These are photos of my journeys around the world using telescopes in America, here in Australia, in New Zealand. Macquarie University has its own telescope, and not only am I using some of the biggest and greatest instruments on the planet, but I get to work with people from all over the world. I get to attend conferences, both nationally and internationally, and it's quite a collaborative environment. We're quite an international environment. And that picture at the top is actually me studying an impact crater. So I don't just sit behind a desk all the time or behind a telescope. I actually get out into the field where I get to do a bit of geophysics, which is looking at impact craters, which are pretty much the craters that are left over when a meteorite hits the Earth. And this is a crater out in the Northern Territory that I was part of a team investigating a few years ago. And so within astronomy itself, you can actually do a wide range of subjects. If you're more an outdoorsy person, you might want to start looking at impact craters. If you're more into cultural components, social components, I'm also part of a research project that looks at Indigenous knowledge and how science is encoded with Indigenous knowledge and culture and traditions. If you enjoy technology, you can work on instrument design and actually design these telescopes and these instruments to use. And if you're really interested in physics in general, there's I've got friends who run simulations on the computers. They love computers. They love designing programs. I've got others who are like myself. We call ourselves observers because we actually observe the universe with telescopes, and we're more experimental. We like to design, come up with ideas and come up with an idea to search the universe for new things. So within astronomy, I've been fortunate enough that I can change the topics I research. I can change fields. I can change countries. Like I said, we're international. We get to move around a lot. And so it actually gives us a wide range of options, which I think exist in general within science, but in astronomy in particular. And so what then does the future hold? Well, these are just some names of some future telescopes that you can Google online. And these are telescopes that are going to be coming online in the next 10 years. So they're currently being built. So as astronomers, we're never quite satisfied with what we've got. We always want bigger and better telescopes. The Square Kilometre Array is an array of radio telescopes that is partly being built out in Western Australia. And part of it is actually being built in South Africa. So that's a huge international technological endeavour. The James Webb Space Telescope is a new telescope that's going to be put up in space. And the Giant Magellan Telescope, which is the picture of it here, is a massive optical telescope that is currently being built. So we're continuing to build new technology and investigate new areas of research. And then I've just got a list of 3 of the sort of up-and-coming, really exciting areas of research. Gravitational waves. You may have heard of this in the news earlier in the year when physicists got really excited at the first detection of a possible gravitational wave. That's going to be a new area of research that opens up when you guys are old enough and getting into university. Obviously, the search for life on other planets is still an ongoing endeavour. And we're also pushing the frontiers with these new telescopes. We're able to peer further and further back into the distant universe, to the early stages around the Big Bang, and investigate what do these distant galaxies look like. And so that's really like a snapshot of where we're heading in astronomy. There's just so much out there, so much to do, that it's endless. So hopefully that inspires you to do astronomy or science anyway. There's so much out there left to be undiscovered. I hope it excites you as much as it does me. And then I've just got a list of a few resources here. The Exoplanet website is actually the website to go to for all the information on all the planets that have been discovered to date. It describes in great detail the different methods. So if you're interested in what I was talking to you about, and I did run through it a bit quickly, please visit that website. It gives you all the details and some information on all the planets, and this is kept up to date very regularly, so you're going to get the latest science straight from the scientists themselves with this website. If you like these tourism posters that I pulled off from NASA's website, we actually have a lot of them up around our own department because they're actually quite cool. NASA is great. Their website lets you download everything for free and print them out, and so yeah, that's a great resource. That exoplanet map I pulled up that shows all the planets in relation to each other, I've got a link there. And probably the most important resource is actually this planetarium software. There's a lot of free planetarium software online, and Stellarium is one I highly recommend because you can download it for free onto your iPads, your computers, your smartphones. And so if you're out at sight at night and looking up at the sky and you want to know, oh, is that a planet? Is it a star? What's its name? You pull up Stellarium and you can actually hold your smartphone up into the sky and it will actually tell you the names and give you the technical details of the constellations and planets and stars and galaxies. So definitely recommend you do that and go outside one night and use that and start learning about, you know, the different things in the universe. We actually name planets based on the star they're found around. So the numbers refer to how, if I've got this correct, Kepler's a bit different. Most of the planets are named after the star. So like Alpha Centauri has 3 planets, so that Alpha Centauri B, C, and D. A is always the designation for the star itself. And so the numbers and the letters will refer to the planet, the sequence of planets, and that's usually how we refer to how a planet is named. Sure. I mean, I really enjoyed investigating that impact crater I mentioned to you before. I did a little geophysics, but I also remember in undergraduate school I really didn't enjoy investigating rocks. So it's a bit difficult because I don't really want to be a geophysicist, but I kind of like doing a bit of that on the side. So I'm actually looking at changing from being a full research scientist into actually a science communicator. So I want to do more outreach activity and write books for you guys and articles for the public. And so it's still part of astronomy, but it's just doing it in a different way and bringing that science to the public. So yeah, I think there's definitely scope within the field itself to change my day-to-day job, but still be part of that whole community and that science endeavour. What happened is the gold that's in here on Earth was actually created years ago, years before, billions of years before even the solar system existed, before the sun existed, and that would have been created when one of the most massive stars blew up, and it would have created all those elements heavier than iron in the periodic table, and then they would have hung around the interstellar medium, and that's the space between stars, hanging out in the galaxy until eventually that giant molecular cloud collapsed and formed the sun and our solar system. So it occurred a long time ago, but yes, technically everything on Earth, even ourselves, we're all made from stardust. Yes, unfortunately, we scientists like to keep classifying and reclassifying objects all the time. Pluto was reclassified as a dwarf planet because our classification scheme for what a planet is, Pluto doesn't actually fit. And so Pluto was actually a captured comet. It's actually very big for a comet, but remember when I was talking about the process of the solar system being formed, all the planets like Mercury, Earth, Mars, Venus, Jupiter, Neptune and Uranus were all born in that circumstellar disk when our sun was born. And a lot of other debris, like leftover rocks, got shot out into space, and Pluto was one of those leftover rocks. So it didn't actually form in that initial circumstellar disk. And there's a few other classifications for what forms a planet, and so that's why we then came up with a new term called dwarf planets. And these are bodies that orbit the sun, like Pluto. There's others called Ceres. There's a whole host of them actually being discovered, and these are really what we call captured asteroids or captured comets, and so that's why it was just reclassified. So Pluto's still out there, it hasn't gone away, we've just given it a slightly different label. Probably breaking the speed of light. The speed of light is the fastest travelling phenomenon in the universe, and our physics tells us you cannot go faster than it. So every science fiction I've seen, Star Wars, Star Trek, I think Battlestar Galactica, all those science fiction movies, everyone's come up with a term for it, like warp speed or going through black holes, anything to break the speed of light and to go faster than the speed of light. So I think that's probably the most inaccurate phenomenon, but it actually gives some really good science fiction stories, so I don't mind it so much. If I remember correctly, it has to be under hydrostatic equilibrium. So what that means is it has to form a nice sphere and be, how do I explain the physics, where it's not sort of changing in size and mass, and that's pretty much, and also where it comes from within our own its formation process. So these captured comets, because they've really got a lot of ice on them, they can heat up and lose that ice into the, they don't have atmospheres, so they lose a lot of that ice. If they go near the sun, it evaporates, and so they're actually changing their mass a little. And so planets like Earth and Jupiter and Mars, we're not changing, we're in what we call hydrostatic equilibrium. Nothing's changing within the actual body of the planet, and so that's really that was the main criteria. I think there were 3 that the International Astronomical Union decided on as a criteria for the planet. It's the only one I can remember. So sorry, I'll have to Google the other 2 for you. But yeah, that would be, yeah, it's a physical, it comes down to fundamental physics really. So. Well, it was really exciting discovering that planet. I would say, oh yeah, that was quite exciting. I don't know. I'm currently investigating gas clouds around star-forming regions, and I'm looking for a particular molecule. I'm actually looking for methanol, which is a form of alcohol. So I'm actually finding this molecule in these regions of star formation. But what's exciting is not so much finding that methanol, because we kind of know it's already out there, but it's that I'm finding it in places that no one's looked before. And so that's quite exciting, because in astronomy we get to look at parts of space that nobody's looked at before. And so my discoveries will be the sort of first time someone's looked at that area of the galaxy and found something. So that's exciting, because I'm really at the forefront of scientific knowledge. So yeah, the molecule's not that interesting, but the area, the space and the regions it exists in is very interesting. So that's probably there. About 100,000, 100 billion stars. If you are out, because you guys are out in rural parts of the country, which is really good because you can probably see some great stars at night. If you go outside at night, like tonight, if it's a clear night, you'll probably be able to see about 3,000 stars with your naked eye alone. And so that's just a tiny, tiny portion of the 100 billion that exist in our own galaxy. And there's about 200 billion galaxies out there as well. So each of them are all containing billions and billions of stars. So it's a lot. The gas, so if you've seen a comet, a picture of a comet, and it has a tail, comets tend to have two tails. One is the tail of the ice evaporating, and one is actually a tail, we call it a dust tail, so the dust even starts to break off from the comet. And that usually happens when it's getting close to the sun because it's heating up. And that actually just goes from ice into gas straight away. So the gas is still out there in the solar system. The molecules might not actually have broken up, so you might still have depending on where it is, you might still have those icicles still floating around in space, or some of the molecules, some of the ice does evaporate off the dust grains and can separate. So they're just still out there in gas or cold gas form, really. Well, to do the research I'm doing, you tend to need to go through university and do a bachelor's degree and a PhD. However, if you are interested in maybe doing something else other than just research, like if you're interested in designing instruments, you could do a bachelor's, possibly in engineering, and go work for a company. If you're interested in designing, if you're more interested in law and space policy, a bachelor's degree is pretty good, so that's about 4 years. If you want to do the hardcore science like I do, you really do need to go through and do a PhD, or a master's at least, and probably a PhD level. So a bachelor's is usually 4 years. A master's is roughly 2, and a PhD is anywhere from 3 years to 7 years. So it's a long time, but if you really love the subject, then you enjoy it. You have to really enjoy the subject to stick with it that long. But at each of those stages you can stop, so there's not that you don't have to continue on. You can still be an astronomer at a bachelor's level. You don't even have to have a bachelor's degree. We have a lot of amateur astronomers, and a lot of the amateur astronomers around the world, that's somebody who just loves space and buys a telescope and looks out at space on the weekends. And a lot of amateur astronomers are actually responsible for discovering comets and variable stars, because they're looking at the sky every single night. They actually know the sky better than we do. So you can still be part of that scientific process without even having to go to university. So it's really up to you what you want to study and how far you want to take it. Thank you.